All right, everyone, let's go ahead and get started. I hope you all can see my screen. Thank you for joining today's webinar. My name is Nate Spurley. I'm a technical sales engineer at RESA. I've been using the ADAPT programs now for several years, originally starting as a consulting engineer specializing in post-tension concrete design. And today we're going to be taking a dive into the most known and widely used post-tension concrete software, ADAPT PTRC. My goal is that by the end of this webinar, you will see how easy ADAPT PTRC is to use and just how powerful it can be. For those of you who are new to post-tension concrete, I'll try my best to lessen any unease you might have regarding these designs. So before we jump into things, please be aware you can connect to the audio using your computer or even by calling in. Also, please feel free to use the Q&A chat box at the bottom to ask any questions you have. We have other engineers standing by to assist. Let's first talk a little bit about the program. The most commonly known product in the ADAPT lineup is ADAPT PTRC, and it's easy to understand why. ADAPT PTRC is a 2D equivalent frame solution that has been around for several decades, which makes it one of the most trusted software solutions available for concrete and post-tension concrete designs. It is truly amazing for one-off calculations, preliminary sizing, and even as a training tool for engineers because it's so easy to use and it guides you through the design process, more or less holding your hand. Now, while you can use ADAPT PTRC to design some moderately complex building geometry, it really is best suited for regular and rectangular geometry, such as a parking garage, which is what we're going to be looking at today. For our parking garage, we have a one-way slab system with beams supported by columns. We're going to assume that that both the slab and beams are post-tensioned. This will allow us to use shallower depths while still maintaining the large spans that you see here, which is usually what you want for a parking structure. So the first step is to split the slab up into X and Y strips. Usually the strips will be based off of the tributaries, but really they can be done in multiple ways depending on how you're going about designing your structure. In this case, I'm going to create a unit strip width for the X direction, since this is the direction of our one-way slab. Notice that the spans for this direction are mostly 20 feet, with the exception being those end bays. You don't really need to memorize the geometry. I have it all on the side here. So when we start getting into the model, I'll have that kind of just on my notes. So don't worry about memorizing anything, but just want to get you familiar with what's going on. For the Y direction, it'll be a simple PT beam with a 20-foot wide tributary and a 61-foot span. Now, in reality, we would need to check more strips than just these two, but only for each unique scenario where the geometry or the loading differs, which, as you can see in this plan, there are a few, but not a ton. But for the sake of time, I'm just going to do these two strips since they are the most typical and kind of can be kind of applied to the entire structure as a whole. So let's go ahead and actually open up PTRC real quick. So I'm going to go ahead and double click the icon. We're going to get a license here. And so the initial splash screen, which it kind of matches my background here, so it's kind of hard to see. We have the option of picking between post-tension and mild reinforced. And as I had mentioned, this is going to be a PT parking garage. So I'm going to select the post-tension option and click OK. And so when the program opens, we're presented with just a blank screen because we haven't started a new project yet. That's easy to do just by clicking this new icon at the top left. So when we click new, now we actually get to see where we can begin creating our model. We have this model space at the top here, and then kind of our input. And I'm going to hopefully drill this into everyone's mind that this program is so easy to use. You're going to be sick of hearing me say two words, easy and the word next, because this program really is that easy and it guides you through the design process. So let's go ahead and we're going to start with our X design or our X unit strip, right? So we'll go ahead and give this a general title. Maybe we'll call it PT webinar. And we'll give it a specific title. Maybe let's call it PT made Easy, if I can type. Awesome. So then we can go ahead and select a different structural system here. So you can see we have a two-way slab, a one-way slab, and a beam option. For our unit strip width, it's a one-way slab. So I'm going to select that option. And then we're going to move over to the geometry input section over here. Now there is this conventional option and this segmental option. The conventional option is really for the situation where your span doesn't vary in geometry, whereas the segmental is the opposite. If your geometry is varying from the beginning of the span to the end of the span, that's where you're going to use segmental. Say, for example, if you had an opening or a jog in this slab, that's where you'd want to use segmental. For this unit strip width, it's all uniform from the beginning of span to end span, so we're going to go ahead and use conventional. We do have the option to include transverse beams. And technically with our project, we had a bunch of transverse beams, but really this option is utilized for being able to put in the geometry of those transverse beams so that the program can take into account reinforcement and that increased cross-sectional area for when we start adding tendons and taking into account our pre-compression and things of that nature. For this exercise, I'm going to just set this option to no, but that is an option available to you. We can also have the program recommend a slab thickness for us if we really wanted to. I like to leave this option as no because then it gives me more flexibility in where we want to go with the design. So really the only thing left for us to do on this page is click next. Easy enough. With the next screen, we get to pick our design code. Pretty straightforward. Let's use the latest ACI. Notice that some of these other codes are grayed out. That's simply because I am working with US units today. You can go ahead and change the units by going up to tools and just convert units. So that's pretty easy. And if I change the units, these other codes would become available to me. Again, we're going to go ahead and click next. Here's where we get to put in our design settings. For the execution mode, we have the option between automatic and interactive. Really what this is doing is this is letting us choose whether we want the program to just spit out a design for us and say, here you go, good luck. Whereas interactive is really going to give us a lot more flexibility when we get to the proposed design from the program, where we can go, you know, thanks program, you did a great job in getting me a good starting point, but I know what I'm doing here. I'm going to tweak this a little bit, or maybe I just want to see what happens when I tweak some of the things as far as number of tendons, the profile, all of that fun stuff. So I'm going to leave it at interactive so we can really dive into that. We also have the option to reduce moments to face of support. I'm going to go ahead and click yes for that. We can redistribute moments if we wanted to. I'm going to use the default no here. The use equivalent frame method, this is grayed out for the one-way slab option that we had selected. And then we can also increase moments of inertia over support if we so choose. I'm going to choose no simply because we're going to be assuming those transverse beams are going to be acting as hinges. So this option really wouldn't be applicable for kind of the exercise we're doing, but it is available to you. Over into the design options section, you can pick to either use all provisions of the code, or you could disregard different provisions. Now, this is really nice. For example, if you are checking an existing structure, right? Maybe you want the program to not add minimum rebar for serviceability, simply because if you're checking an existing structure, it's already built. You can't change the amount of rebar, so you can suppress the program from adding additional rebar to meet serviceability requirements there. And you can do other things such as, disregard design capacity exceeding cracking moment, contribution of pre-stress and strength checks and things like that. But I'm going to go ahead and use all provisions. There's another option to include this extra load combination based off of the UBC. I'll just leave that off. And then we could generate moment capacity based off of either design values or user entered values. Again, this kind of goes back to the example of maybe an as-built condition where you're wanting to check the capacity of a slab, maybe with loading changing, for example. Here we could include the all sections for the pre-compression or RP over A, for example, for those transverse beams. like I had mentioned earlier, where we could put in the geometry. Again, since we selected that no option and we're not going to have any drop panels or drop caps, this isn't going to do anything for us. So I can go ahead and leave it off. We'll go ahead and click next. And here's where we get to start putting in our span geometry and start to see something in our model space. So we had 15 spans for the unit width direction. So I'll just go ahead and click this up to 15. And you can see the program's populating all of these individual spans. Now, really nice feature within PTRC, which makes it a lot easier for everyone to use and kind of get a handle on, is we have a lot of useful diagrams that help you understand really what's going on within the input, as well as a legend. And then it's also really important to pay attention to your units, right? Sometimes things will be in feet, sometimes other things will be in inches, sometimes things will be in kips. And so it's really important to pay attention to those units so that you're not modeling your structure with unrealistic sizes. So if you recall, most of the spans for our unit width direction were 20 feet. So I can type in this 20 feet into the typical row here, and it'll be applied to everything. Now, looking at kind of our legend and diagrams up here, we can see that the B is referring to the width of our strip, and we're using a unit width strip, which is 12 inches. So I'll type that in. And then I'm going to go ahead and assume a thickness of about 5.5 inches. This is just kind of a preliminary hand calc that I did to get us a good starting point. Right. And so if I go to the top here, we can zoom extents and kind of see our really long unit width strip kind of coming into play here. Now notice there is the ability to include a left cantilever or a right cantilever. You can check that option on. You could also change the section type by simply clicking on the section. And then if you change the section type, obviously these other parameters would become available to you based off of kind of these different shapes. If we go ahead and look at our model now, we're not going to see much of a difference since it's simply 12 inches wide. But if I zoom way in here on a top-down view, I believe I was on a top-down view. Now I'm on a top-down view. We can kind of see, okay, yeah, we got that 12-inch width. The side view, we have that 5.5-inch depth. And if you notice, oops, didn't mean to rotate there, sorry. If you notice, we have the 0 here, and this is our datum. And that's kind of what this next column is talking about. And in PT design, when you start getting into your drafting and detailing, typically the tendon heights, the CGS or the center of gravity of steel, is referenced from the bottom of the slab. And right now with our datum being at the top of the slab, all of our CGS values are going to be negative, which really doesn't make sense. So what we often recommend is typing in your actual slab thickness or beam depth in this field. And you'll notice it bumped that datum down to the bottom. And now all of our tendon heights will be referenced from this datum with a positive number. Now, if we switch to a top-down view again, and we're looking at this first span, we're going to talk a little bit about these left and right multipliers as you can see here by the legend. Now, imagine you're standing at this position near span 1 and you're looking towards span 15. Your left hand is going to be pointing in this direction and your right hand is going to be pointing in this direction. And that's kind of a good way to orient yourself with these parameters. Now, what these are doing is they're acting as a multiplier for your slab width. And in this case, we have 50% of the slab width, or in this case, B, which 50% is 6 inches. 50% is going to be on the left side, and 50% is going to be on the right side. Now, maybe we go through the design and we go, okay, yeah, we had a unit strip width of 12 inches. Maybe we want to increase this a little bit and see if our results change. We can go ahead and bump this up. So if you pay attention to the left side of span 1 here, and if I change this to 2, for example, you'll see it increases. So now we have 2 feet of slab on the left side and 6 inches on the right. I'll go ahead and change this back. This would also be useful, for example, say if you had jogs in the slab or openings, you can shift the amount of slab from center line. And what we would recommend at that point is just make sure that these add up to 1, because then you're not increasing the width of your slab, you're simply shifting it. Awesome. So I think that takes it out. We need to adjust our geometry. I almost forgot. So that first span was 26 feet. So we'll increase that. And then our second to last was 24. And our very last was 22, I believe. So if we zoom extends on the side again, we can kind of see that coming into play with our different spans. So let's go ahead and click next now. Here goes where this is where we can put in our support geometry. For an example, we can put in lower walls or both walls. The both walls would be lower and upper walls in this situation. If we had a two-way slab scenario, this would be columns instead, right? So right now we have transverse beams. So I'm going to keep these as kind of point supports or a transverse beam option. But if we had walls in this situation, you'd enter the parameters down here and just use the legend. That's pretty straightforward. Now, something really not so obvious is this left edge and right edge option. This is really useful for your punching shear situation. So for example, if this was a bay on the extreme side of our structure, perhaps the left edge is technically the exterior edge of the slab. And by changing this option to exterior, the program is then going to check 4H away from that support for punching shear reasons, right? If you leave this as interior, it's just going to assume that, hey, we have enough critical section, we'll do the punching shear check. So this is really important for whatever condition your columns have for punching shear. Let's go ahead and click next. Awesome. So let's go ahead and start putting in our boundary conditions for this. If you had this structure kind of tying into, for example, an existing building, or for some reason you had fixity on this side, you could say, yes, I'm going to have some fixity, or no, I'm not going to have fixity. Same with the far right side. That's not our situation here, so I'm going to leave those both as no. Here you can see kind of the legend as far as what the different boundary conditions are, simply based off of 1 being fixed, 2 being pinned, 3 being roller. And you'd put those in kind of these different cells down here. And you can see this little useful diagram here in reference with this LC, which refers to lower column, or in this case, lower wall, and then a far end and near end. And then conversely, this UC, which is upper column or upper wall, you have a far end and near end. And that's kind of where this table is describing that. Now, this SW is a support width, right? And this is really nice because this is going to tell the program to trim our shear, moment, and stress diagrams near our center line of supports, right? So if we have a moment diagram going like this, we're going to have a peak of moment right over that infinitely small pin location, which isn't necessarily realistic. We have some width to this support. And so we want to really check those moment shears and stresses at the face of supports. So I can quickly just assume that our transverse beams are going to be about 18 inches wide. So I'll type in 18 inches there. And this is assuming now, or trimming our diagrams 9 inches on either side of the center line. So that's pretty easy. We'll go ahead and click next. Awesome. Let's get into some loading. This screen has a lot of information. So I'll try and keep your attention as we're going through this. Again, important things to notice: units, right? Pay special attention to units. I can't tell you how many times where I just go through a design really quickly in this program, since it's so easy and quick, that I forget that this is in kips and I type in pounds thinking it's pounds, and then all of a sudden, whoa, my deflection is astronomically high. There's something wrong. And I go, oh, that's my mistake. So again, pay attention to your units. Legend, of course. This is really useful to kind of understand the notation here. Over on the right, we have the option to include a skip live load. I'm going to turn this option off just because it'll help us really see the results a little bit better and not have to kind of wrap our head around, okay, well, now we have live loading on this span and this span, but not that span. What is really going on? I'm just going to turn it off so we can kind of really grasp what's happening with our model. You can have the program and include self-weight for us. I'm going to have it do that. I like that option. I don't want to put it in there by myself. So let's go ahead and use that. Now you can see the different types of load combinations here. Now, or not load combinations, sorry, the load types. We have uniform loads, partial uniform, concentrated, point moments, line loads, triangles, variable, and even trapezoidal loads, you name it. There's a lot of flexibility here. And it's as easy as just picking a span, selecting your load type, whether this is superimposed dead load, live load, or this X wildcard, which can be any load type that you want. Maybe you have roof live load and you want to use that in your model. That's where you could put this. And then later on, you can specify the factor for that X wildcard when we get to the load combinations. So I'll just select superimposed dead load for now. And we can actually specify the load type by one of two ways. We can simply grab this picture and drag it over to the cell, just drop it in there, and you can see it's this uniform load. And then we could go ahead and type in the area load that this is. Or the other option, which I really like, is, let me delete this real quick. The other option is you can just type in the second letter in these load types. So if I want a uniform load and I simply press U on my keyboard, it just grabs it for me like that. Now I could go ahead and just start adding my load for superimposed dead load, go to 2, span 2, do my superimposed dead load, but that's going to take me a minute, right? And so a real quick and handy feature is just to use the word all. We're going to do superimposed dead load, uniform load, and we'll do 20 PSF dead load. Let's go ahead and change this one to all as well. And we'll put some live load in here, again, pressing U on my keyboard. And then let's do 40 PSF live load, right? We're not seeing any loads generated there yet. So if I press next and then go back, we can see all the loading being added there. I can kind of zoom in. Oh, sorry, my computer's running a little slow. And zoom in there, and you can kind of see the loading. Notice it filled out this table real quick. Let's appreciate just how easy that all tool is. Saved me a bunch of time doing that. Now, there's also this label column, which I kind of skipped over. This is really nice if you have a bunch of unique loading kind of going on and you want to kind of label your loads just for bookkeeping and reference so that when you come back later, you go, what was this point load for? I can't remember. You'll know because you have a label there. So that's a really nice feature. Let's click next. All right, so now we're going to start specifying material properties within our model. I'm going to use a normal weight concrete with a 5,000 PSI strength. And notice if I just type this in and click, our modulus elasticity doesn't update. If I actually type it in and press enter, you'll watch our modulus elasticity update. Really nice. Program likes to help you when it can. So use that feature. Makes it easy. Our concrete strength, typically this is the initial concrete strength, sorry. And this is typically about 70 to 75% of your overall concrete strength. I'll be a little conservative and use 70% here. So that's about 3,500. Go ahead and click next. Now we're on to our mild reinforcement. We're going to use a 60 KSI yield strength for our mild steel with a modulus elasticity of 29,000 KSI. We're going to have a preferred top bar size of a number 5. And I'm actually going to change this bottom size to a number 5 as well, simply because our slab is pretty thin. So we'll go ahead and do that. Here's where you can specify your shear reinforcement. In this case, stirrups. We're not going to really get any stirrups for this unit width stripped, but you can do that, and also the number of legs. So let's go ahead and click next. Now on to our post-tension material. You can pick between bonded or unbonded simply by using this radio button. I'm going to go ahead and assume a 1/2 inch diameter tendon with an ultimate strength of 270 KSI. And then I'm going to specify an effective long-term stress. This long-term stress of 175 KSI that I put here is the average stress that we're anticipating the tendon to exert onto the slab after all of our losses, such as friction, elongation, and seating. Now, there's two ways you can kind of go about using the program. You can either use an effective stress, where we just assume the losses are going to be roughly this, and then get a design, or you can actually have the program calculate those losses for you, where you put in the friction coefficients and seating loss and all of that. And I'll talk about that here in a second, a little bit more. If you notice, we take this 175 KSI as the effective stress and multiply it by our area, we're getting about 26.7 kips per tendon. Let's click next. Here you can put in base reinforcement if you want, right? If you say no, the program's still going to give you reinforcement where it's needed, but perhaps for a project, you'd like to just specify a certain type of reinforcement for certain situations, just to kind of as a warm blanket for your designs. All right, you can do that. You can go ahead and put in a mesh or isolated or even stirrups. So for example, if I do isolated bars, we specify the first end location. In this case, let's say I wanted it at span 1. We probably won't be able to see it since this model is so long, but we'll go ahead and zoom out so we can see everything. So first end location is 1, and then this is a percentage of the span. So if we wanted to start right at kind of the 0 mark, we'd put in 0 here. And then the end location we could say is span 15, for example. And then this would be a ratio of 1 so that it goes all the way to the end. We could then say a bar size, maybe we're using a number 5. And how many of the bars? Maybe we have 1 since this is a 12-inch width strip. And then we can specify if it's top or bottom. Maybe we have a bottom bar all the way across there with a 1-inch cover. Right, very easy, and you can get really creative with your rebar, probably more than you'd ever want to. As I scroll down, I'm already over 100 lines of different rebar you can put in here. So go wild if you want with that. I'm going to go ahead and let the program calculate the rebar for me. So I'll select no. And we'll click next. And here we're getting into the criteria of our model. This is where we specify our tension stresses as a factor of the square root of F prime C. All right, so we have our 3 root F prime C for our initial, and then our 7.5 square root F prime C for our sustained and total stresses, top and bottom tension. So these are just pulled directly from the code that I had selected. You can adjust these maybe if you have more strict stress requirements. That's why this option is here. And then obviously compression stresses down here. I'll go ahead and use the defaults and click next. Here we're at average pre-compression for the program to target. All right, I'm going to use 125 PSI, which is the minimum code required. But I'm going to tell the program, hey, don't go over 300 PSI. That's an upper bound for me. We can also tell the program to balance a percentage of the dead load for us. All right, we can say, hey, minimum balance 25%, but as a maximum 200%. Now you got to be careful kind of narrowing these in together, because by doing so, if I just said 100% and 100%, I'm not giving the program a lot of flexibility to come up with a design, and it may say, hey, you don't have a solution, or nope, we can't find anything that's going to work for you. So be careful with what you're putting in to this criteria window. It can really impact kind of the output that the program gives. You can also specify the maximum spacing between tendons, right? In this case, 8 as the a multiple of the slab depth. In this case, 8. We only have a 12-inch width, so this isn't going to be a problem. But that's nice that is in there. Here's where we can pick whether the program is using that effective force that I mentioned earlier, or if we want it to actually use the calculated force, right? So if I select calculated force, we can specify the ratio of jacking stress, the modulus elasticity of our tendons, the angular coefficient, the wobble coefficient, and even our seating loss. And then the long-term losses, we can say, hey, we're just going to use an estimate. Maybe this estimate is 10 PSI. Or you can actually have the program calculate that long-term loss for you, whether you're using a low relaxation strand or a stress relief strand, based off of the age of concrete when you stress, the modulus elasticity at stressing, the relative ambient humidity, and the volume to surface ratio. And then even if you're stressing all the tendons at once or just one of them. So I'm going to go ahead and use the force selection. This is typical for US engineering firms. I'm going to assume that the PT shop supplier is going to be the one that does all of those loss calculations for me. So we'll click next. This is where we get to put in our tendon profiles, right? So this is really straightforward and similar to kind of the other windows we've seen, right? You have kind of this key of 1, 2, 3, 4, 5 based off of the tendon profile, and then our spans. So maybe we had a big point load coming down on span 7 and we wanted to use the HARP parabola. It'd be as simple as just changing that here to HARP parabola and adjusting kind of where that location is based off of the X2, right? We don't really have any crazy loading going on, so I'm just going to assume a reverse parabola for all of the spans. And again, you could change the inflection points for each of these tendon profiles, kind of using this X1 over L, X2 over L, and X3 over L. Now notice there is a tendon B and tendon C profile. Right now, we're assuming a tendon A profile, which is going all the way from the left side of our structure to the far right. Tendon B and tendon C tendons, they are more of an add tendon, which you can specify anywhere within your slab. Maybe it's only on these end bays, or maybe you have a pore strip and you need some additional tendons or things of that nature. That's where those come into play. And you have some of those parameters down here for those tendons. We'll get more into those when we get to the design window. So click next. Here we specify our cover for our tendons as well as our mild steel reinforcement. I'm just going to go ahead and assume 1. Obviously, these can vary depending on your fire rating and other requirements. Click next. Here we have the criteria for our rebar. The top section is for our service, right? This is a percentage of the span of how long our service rebar needs to be. The bottom is more for strength, and you can kind of look at this as our development links, right? So right now we're saying, hey, we're going to extend our strength reinforcement 12 inches past that point of zero moment. We'll go ahead and leave those as is. Here is the reinforcement curtailment window. So this will let you do more specification as far as rebar lengths, right? So you can see you have the ability to change rebar lengths for cantilevers, exterior spans and interior spans, and then you can use different rules. For example, you can just say, nope, I don't want any curtailment, or you can set up your own. We also have an adapt one. This one is just grabbing the previous values we put in on the last screen. But I'm going to go ahead and use the ACI 318. And you can do that for both top and bottom bars. So click next. Now we're to our load combinations. You'll see we have a total of 4 strength load combinations that we can put in to the program, with 2 kind of being filled out automatically for you based off of the code we selected. And notice there's that X wildcard we talked about when we were on the loading screen, right? Right now it's going to be 0 because we don't have the load, but you can put those factors there. There's also 2 sustained load combinations that you can specify, with 1 being brought in by default. Again, with total load, we also have 1 combination, and you could specify another if you would like. Then you also have the ability to input your different strength reduction factors if you want to change these, right? We have 0.9 for bending, 0.75 for one-way and two-way shear. Oh, and I almost forgot, we have our initial load combination for checking that initial condition of our concrete not being fully cured yet or achieving its full capacity strength. So here's that load combination there. Now, we do have the option to include lateral load combinations and factors. So if I click this include lateral loads and set the values, I can go ahead and go in here and you'll see we have some additional load combinations, two to be precise, with lateral factors included. You can go ahead and change those. I'll use them as default. You can also say, hey, this is the sign on these lateral moments is changing direction. Maybe I have wind in the X and wind in the negative X. So I'll go ahead and say, yes, let's do that. And then you can specify the PT to resist factored moments as a percentage. So we'll keep that at 100%. And then when we click on the lateral moments tab, this is where we actually put in the loading from our lateral. Now, the way you'd have to go about doing this is doing a hand calc to figure out, your unbalanced moments or your moments due to lateral, and then put them in here. But once you've gotten them, it's pretty easy to input them. Maybe we have, for example, a 40 kip-foot moment kind of at this span. And notice you have the sign convention and notation here. So if I just go here, maybe we have 20 on this side and 20 on this side. All right, and I can zoom in here real quick. Oh, or not, I didn't select the tool. Zoom area. There we go. You can see those point moments going right on either side of that support. Now, I just picked those arbitrarily. I have no idea if they're going to work. They may be way too big. They may be way too small. Just something to throw in there. So we'll click OK. Let's zoom extents real quick. Now, notice there's no next button. There's nothing else for us to input into the program. So we have generated our model. So I'm going to go ahead and click the execute button at the top here. It's kind of this little grid icon. It's going to ask me to save this. I'm just going to grab my desktop and throw it on there real quick. And we'll click save. And now the program's going through the analysis based off of all of the data input, right? We didn't have to jump around in any way, shape, or form. We simply just went to a screen, put in the information, click next, put in the information, click next, so on and so forth. And then we get to the end and we simply put in our, or we get to the end and we simply execute the analysis. And it looks like it pulled it up on a different screen. So let me pull that up. And it's done. So here, this is what we call the recycler window. And you can kind of see an overall status of the design up here. We have several OKs and a couple of no goods. So we go, okay, well, what's that about? Right? What's happening here? Now, I'm more of a visual person. I could go through and look at these graphs, but to kind of make it easier on myself, let's go ahead and open the graphs. And so we can see kind of just a general layout that the program has, general layout and design that the program has given us, right? We can see our tendon profile up here. We can see the stress diagrams in the middle, and that's simply, we can change how that is being shown here. So right there, we're showing the bottom fiber for the total load combination. And this may be a little small. What we could do is let's deselect all and maybe just turn on a couple of the spans, right? Let's turn on a few. And what's nice is these graphs are interactable. So I can actually click, for example, this tendon, the low point, and see, hey, my center of gravity of steel or CGS is 1, which is what we specified, right? We specified 1 for that. We could also do the same thing for these graphs, but looking at this a little bit and turning on more spans, it looks like this first span is really controlling. And in fact, the end span is as well, if you noticed. And that's largely because it's such a long span, right? And so this tells me that there is the ability to optimize this design because we're not seeing any tension stress in the middle of these spans for the interior of our structure. So I'll go ahead and close this, but let's go ahead and dive into kind of some of the information over here. So if I click on the extreme fiber stress tab, I go to total load. Okay, yes, we can see, yep, there it is at the center of span 1. our tension stress is at 7.5. The program brought it right up to code allowable. And as I thought, that is the controlling span. And we can see that even more because everything else is zero. Everything's in compression, which is not good for us. So we could keep adding PT to potentially try and mitigate this. But I think the other issue is our PT force is saying no good. So if we go back to the first input screen, we can see our total pre-compression or P over A is at 345. And we set a limit of 300. And so if we go over to the total force column here, this is how much we're supplying, and this is how much is required, right? So we need 23 kips, and we're supplying 22.8. So with some rounding, we're at that 23, but that is really high. So for me, I think this span is just too big for how thin the slab is. So let's go ahead and adjust that real quick. If I click this edit data button at the top, this will throw us back into our model. And I could go ahead and click next and get through everything, or you can use the menu at the top. So I'm going to go ahead and click geometry, go to span geometry. We're going to change that first span to, let's say it's 8 inches. And if you pay attention to the model space up here, you'll notice that it gets updated. Kind of zoom in there. You can see that slab is actually thicker there. So with that changed, let's go ahead and execute the analysis. Again, we're going to go through all of the loading and all of the spans with this now newly updated geometry. Oh, and I forgot to adjust my reference height. That's okay. We're going to have one of our spans with a negative profile or negative CGS for our tendon, but that'll be okay. So we'll go ahead and say, yes, we want to save. Now we should have results here in just a second. And hopefully this will be closer to the, it looks like it showed up on my other screen. Where did it go? There it is. Hopefully this gives us a more realistic or acceptable design. And as you can see, we're green okays on everything. And looking at kind of this total pre-compression here, we're much lower. Obviously it's less because we have a thickening on that first span. So we could be done. We could say, yeah, this design's okay. We can just run with this. But with my experience, I'm going to see if I can optimize this a little bit more. So if we go back into our graphs, we can still see, hey, we're still not experiencing any tension stresses in the bottom of these interior spans. So we have technically too much PT in the middle. And that's easy to see here as well, right? The required force for these interior spans is only 8 kips. But since we're using that tendon A and it's saying, hey, we need actually 14 over this one, it's being applied to all. So where I'm getting at is going back into the add tendons. So what we can do is select this tendon section and extents portion, and we can actually just drag this tendon and we can add them wherever we want. You can also change the ends by shift clicking. If maybe one of them is dead and one is stressing or both are stressed ends, you can do that. Now notice the program is saying, hey, you need to recycle. And that's because I have changed some of the data within, this input screen. So this is not necessarily the most up-to-date information. Now I haven't changed anything as far as tendon forces, but I've changed the tendon extents. And so the program is warning me. So if I click recycle real quick, it'll just update everything and we'll be good there. All right, so now we have those tendons going kind of over those first 2 spans. So let's go ahead and adjust this. So instead, what I'm going to do is say, hey, I only need 8 for the interior span. So let's type in 8 here. If I press enter, you'll see it updates all the spans because it's a tendon A, which goes from all the way from the left to the right. And again, the program's saying, hey, you need to recycle because the results are not current. Now, before I do that, I get a little preview here and I can see that my pre-compression is only going to be roughly 121, which isn't enough. We need 125. So I'm going to bump this up. I think I need technically 8.3 to just get over that 125. You may want to go a little bit higher for some wiggle room and some cushion there, but we'll do that. Now, if we go to tendon B, for example, this is going to be the tendon on the left side. And so we need to bridge this gap between the 8 kips and that 14 kips. So it looks like I'm going to need about 6. So if I just type in 6 there, press enter, you'll see, hey, you're going to have an additional 6 kips on span 1 and span 2. Now we'll switch to tendon C. And this one doesn't need quite as much, but I'll be nice to our builders and just do 6 as well so that they're not mixing up one side of the building or the other. So that looks good. So let's go ahead and click recycle to get updated results based off of the tendon changes we did. And there we go. Now we can see a little bit better that, hey, look, we have some tension stresses in the bottom of our spans. This is much closer to what we are expecting, or it's much more optimized, right? We're utilizing this capacity that we have. We are able to have some tension stress here. And you can even see over on this far end that our pre-compression is a lot more reasonable, right? There is this one area that the pre-compression is high, but it's not every single span. So we're using a lot less PT in this case. And maybe it's a trade-off as far as, hey, the constructability of this is going to be much more difficult, right? Because we're having all these ad tendons versus a material cost. So I'll leave that to you guys to determine, but I'm liking this design. I think it's much more optimized. You can see the actual required tendons in this bottom graph, all right? If I turn some of these off, the required is in green and the provided is in blue. You can see it drop down. And kind of what I can infer from these graphs is that really these interior spans, they could be wider if I really wanted to. And ultimately what's controlling this is the pre-compression, right? We have all this extra wiggle room, but if we lower the amount of tendons, we're not going to meet that minimum 125 pre-compression that we need. So I like this design. So let's go ahead and click exit. We can really drill into the results of this. So by clicking exit, we're going to get to graphs, deflections, moments, all of that good stuff. So if I go ahead and go to the top here, I can click show graphs, right? And this is our tendon profile. Again, there's a lot of spans here, so it may be a little jumbled, but you can kind of turn those down and get an idea of, hey, this is our profile. You already saw this on the last screen, so nothing new there. Here's our post-tension required versus provided. Again, you saw this on the last screen. This is what I was just talking about. So nothing new here. We'll close that one. Stresses, this is similar to that graph once more. So I really like the bottom stress graphs here and the top stress graphs to kind of show you the allowable versus the service envelope and whatnot. So we'll close that. But this graph is actually new, and where we can see our deflection. And it does look like we have a little bit of an issue here, which doesn't surprise me. This would be an upward deflection, right? And it doesn't surprise me because of this huge span. It's actually causing this to deflect upwards. And I could go back and adjust my tendon control height. If I have some stress wiggle room here, I could do that and try and lower this. For the sake of time, we won't do that. But what I really like to do is actually show on or turn on the deflection due to my PT versus, for example, my self-weight or my superimposed dead load rather. Right, so let's turn on self-weight. And you can see, hey, the tendons are trying to cause an upward deflection, whereas obviously the superimposed dead load is trying to cause a downward deflection. And it looks like these peaks are exactly opposite of each other. This one might be a little off, but this is how we really can tell that our PT is helping us, right? Close that. Here we have our shear diagram, right? And you can turn it on for different portions, whether it's live load, self-weight, all that fun stuff. And then bending moments, right? And again, kind of the same inputs. Now, if we go to the top, there's this builder sum option, which is personally my favorite area to look at the results. So by clicking on this, we can see things such as our force diagram again, nothing too new here. We can also see our moment diagram. Once again, not anything too new. We'll close that one. Stresses, again, very similar to what we've been seeing. But the rebar diagram is new. We can see the provided rebar is kind of the solid line here that kind of steps up and down, and the required is this green and blue. And you're going, well, what's going on there? My best guess is probably those point moments that I put in. They're probably a little too, they might be a little too large. My estimate may have been off on that one. So we have a lot more rebar required in this span, right? So that would explain that. Now, my favorite part of the builder sum report is this summary report. And I'm going to trim this down a little bit so we can kind of see some of the results. So let's go ahead and maybe just show 8 spans or 9 spans in this case. And you can see the tendon profile, the rebar, and it looks like we have one number 5 for each 12 inches, right? Which makes sense. So right now we have about a number 5 every 12 inches. And then obviously we have some increased rebar over that location where we had all those point moments. We can see the actual tendon profile with the CGS or the center of gravity of steel here. And all of these are making sense except the one that I forgot to adjust the datum, right? This is now saying 1.5 inches below the datum, which was 5.5 if you recall. So that's 7, which then means we actually are 1 inch from the bottom of the slab. So that is correct there. If we keep scrolling down, we can see the forces. Again, more drape. Here we have a force per width. Obviously, this is going to be exactly what we put in since we're at 12 inches, but this is really nice if you're doing a wider strip. And you can tell the shop supplier, hey, I need this amount of force per foot in this location. Here's the bottom rebar that the program is saying we need. And then again, this kind of similar graph for the provided rebar, which is this blue line, versus the required, which are kind of these vertical purple lines here. We don't have any shear stirrups, so that area is, we don't have any shear reinforcement, so that area is blank. Design parameters that we had set, material quantities, and if we go to the next page, we can see a much more detailed output of our deflection with the different deflections for our load cases, as well as our span to deflection ratios in parentheses. Awesome. So we did this X direction. The next thing would be to, I'm going to close this. The next thing would be to do our Y direction. Instead of going through that process of clicking next and talking about how easy it is, you guys would be able to fly through that beam in probably a couple of minutes now that you're experts with it. So I'll just go ahead and open it real quick. Let me see, I have it up here. So here's the beam that I had created. So we'll go ahead and open this. And what's important to know is when you open up a model in PTRC, you can go to the recycler screen, which is kind of this little recycle window or emblem, right? And when you go to this recycler window, it's going to say the design is current. Now, it's really important, and in this case it is, but it's important to hit the recall button because the program won't recall the last input that you had saved unless you hit recall and then recycle. So that's an important note. If I opened up that strip width one that I did, it would default to a tendon A everywhere at 200 something pre-compression. So that's important to note. Really though, with beams, there is only a few differences. So I shouldn't have closed that. It's going to open up all of our graphs. But if we go into the input, really, it's not super different, right? You click through next, and do all this fun stuff. What is different is since this is a beam, the program will be able to actually ask you if you want to put in an effective flange width, and it'll calculate it for you based off of the different codes. So this is nice, and you can override it if you want. So I didn't have to put any of this in. I simply put in, hey, it's 20 feet width, and this is my span length, and it did all of the different effective flange width calculations for me. And then here, the only difference is actually having our columns, right? So I've specified some columns in this model for us to use as supports, right? So I can kind of zoom in here and you can see them just like that. So let's get back to the execution screen real quick. Sorry, it's going to run through the analysis real fast one more time. But we're going to go ahead and look at kind of some report generation and see what the reports look like, right? Reports are important for us to explain what we've done and portray that, hey, this is an adequate design. So again, here's kind of the design for my beam. I can click exit. It's going to bring up the graphs for the design. But what we can do is we can actually go up to this report generation button up here. So we can set up a report. And this is really nice where you can just simply select a report cover or pick and choose any parts of the report that you prefer. I like to do, for example, the concise report and then all of the graphical reports, which is kind of all those graphics we've seen, right? And so instead of me generating this and us waiting a couple of seconds for it to load, since we are running short on time, I generated it beforehand, and I'll just open it up real quick. We can kind of take a look at what this looks like. All right, so if I zoom in here, right, I have my title that I'd put in on my geometry screen and all of, a preview of what we're looking at, a table of contents. Scroll down, we have all of our project parameters, the load combinations, the geometry, the dead load, the live load that we input, moment diagrams, and obviously all these you can manipulate these, right? Maybe this is a little too small for our report purposes. You can blow that up a little bit. So all of this is kind of the data we've looked through and taken a look at in the program, but it prints it out really nice for us to take a look at and present for submittals. So shear reinforcement for this beam, for example, right? So we can see all of that, the max versus the spacing and all of those fun parameters. Stress diagrams, shear, deflection for all the different load cases. And again, these are all tailorable to what you need just based off of kind of what you select in that output screen. So I'm just kind of flying through these just to give you just a little preview of the output that the program can do, right? So it's really nice. Anyways, let's get back to our PowerPoint. Awesome. So thank you everyone for your attention during this presentation on ADAPT PTRC. I hope you learned something new today and that I demonstrated just how easy post-tension concrete design can be using ADAPT PTRC and how it just holds your hand through the design. PDH certificates will be emailed directly to you within the next few days. You'll also be able to find a recording of this webinar on our YouTube channel. So if you want to refer back to it, you can. Should you have any questions or want to learn any more, I invite you to email us at info@resa.com, or you can visit our website at resa.com. We have an amazing support team. If you didn't get to answer your questions here, I know they'll be happy and more than willing to answer your questions. So feel free to ask those away. I'm also available to answer any questions that you may have. Again, thank you all so much for joining us and have a great rest of your day.